Mr. Ains, we're here to start you off with Chapter 9, which looks at testing a claim. And in this video, we're going to focus on Lesson 9.1, which represents the basics of significance tests. Now, don't get misled by that word basics. That doesn't mean the easy part of significance tests. It means the foundation for significance tests. Now, we're going to look at the first two objectives in this video, which deal with stating the hypotheses. Notice that is plural. You're going to have two of them for a significance test for a population mean or a population proportion. So notice those are parameters. You're going to interpret a p-value in context. So we're going to have to define a p-value. What does it mean? And learn how to interpret it based off of our results. So in order to move forward, we have to look at where we've been, because confidence intervals and significance tests are the two most common ways to perform statistical inference, and they have different goals. The goal of a confidence interval was to estimate an unknown population parameter, such as mu or p. So we didn't know the population parameter mu or p, and we used a sample. We created an interval from that sample, and we hoped to capture the population parameter with that. For a significance test, it is different. The goal is different. Its goal is to assess the evidence provided by data about some claim concerning the population. So in this case, for significance tests, we will have a claim about the population parameter. And we're going to assess the evidence provided by data about that claim. So a significance test is a formal procedure for comparing observed data with a claim whose truth we want to assess. And that claim is called a hypothesis. And the hypothesis always deals with the population parameter, p or mu. When we express the results of our significance test in terms of a probability, maybe that has something to do with p-values. So you saw that in the objectives for today, hypotheses and p-values. And what that probably does is it measures how well the data and the claim agree with each other. So really, here's an outline of what we discussed. And what it is that there is a claim about a population, and we're going to call that our null hypothesis. And we're going to have a question. We're going to question that claim a little bit. We're going to suspect something's wrong with that, and that's going to be our alternative hypothesis. We're going to perform a test about it, and we're going to look at the results of that. And those results are expressed as a probability. I want to apologize about that. That was my friend Lloyd. He met a woman, Mary, on Valentine's Day, and he really, he says he's absolutely in love with her. And he says that he thinks that she's in love with him the same amount, and he's about to confess that love to her, and he's saying that she feels the same way. So I apologize for that, because that has nothing to do with what we're looking at when it comes to significance tests. So we were talking about null, alternative, and p-value. So the null is based off of a claim. Well, actually, that's interesting, because Lloyd, he claims that Mary loves him as much as he loves her. I mean, that is a significance test. So he claimed to me that Mary loves him as much as he loves her. That's the null. Now, I know they met a week ago. So I'm suspecting that her love for him is not as much as his love for her. So that's the alternative hypothesis. I think something's wrong with that. And so he's about to tell her. There's the data collection for us. And her decision is really going to be the probability level, the p-value. So it turns out, hopefully Lloyd doesn't care about this, but it turns out this situation with Lloyd and Mary, it relates to significance tests. All right, so I'm going to go on with this Lloyd and Mary thing because I think it's really interesting. I actually wrote down right here some null and alternative hypothesis for you. A null hypothesis and alternative hypothesis, that's how we label it. And this says, heart for M, so the love of Mary equals the love of Lloyd. And that was his claim when he was texting me. That was his claim. The alternative is I suspect something different. I really think her love is not as much as his, that it is less than. So there's my hypothesis. And so if we're in Lloyd's world on this, Lloyd would love for it to be right here, where Mary's love for him is equal to his love for her. I suspect that her love is less than his love. And so that would be way over there. Now, if her love was more than his love, I still think my friend Lloyd would be happy. So I'm suspecting less than. I'm thinking that it's over in this area over here. And really, that's what we're going to be doing with significance tests. When things are closer to the middle, that's really fitting what the population says, what the null hypothesis says. But when things start going out, in this case, to the left side, it's not lining up with what the claim is. So the goal of a significance test is to assess the evidence provided by data about a claim concerning the population. So there's a claim about the population. Lloyd claims Mary loves him as much as he loves her. We're going to assess that evidence provided by data on is that statement true. Let's use this basketball example to help us out. Suppose a basketball player claims to be an 80% free throw shooter, and we suspect otherwise. We suspect that's not true. So we have him take 50 free throws, and he only makes 32 of them. So in that case, his sample proportion, p hat, equals 32 out of 50, which is p hat equals 0.64. So there's really, in the case, the claim is that his null, p, equals 0.80. And if we look at this, what this simulation down here, what this distribution is 400 sets of 50 free throws, given that the null was true, that he really was an 80% free throw shooter. So this dot plot, each one of these dots are p hats, and it's assuming that his probability is true. And you can see that because a lot of the p hats here are stacked in the middle. But notice what we observed. We observed this point right here, which is your p hat of 0.64. And if we're shocked that he made 0.64, we would be even more shocked if 0.62 was his probability from a sample. So we're looking at as few or less. So we're looking at towards the tails here on what he did. And what we observed, should that have happened if this really was true? So if he really is an 80% free throw shooter, we are more likely to see these events, and we are less likely to see these events. And that's really what our hypothesis test is going to do. You can say how strong the evidence against the claim is, against the null, by giving the probability that he would make as few as 32 out of the 50 free throws if he really was an 80% free throw shooter in the long run. So we saw here 3 out of 400 times that something occurred at a probability or less than that probability. And that is so small, that's less than 1%. So our observed statistic is so unlikely if the parameter was true that it gives evidence that the player's claim is not true. And that's a very weird thing to say, but you need to realize what we witnessed is so far out here in the tails that we probably should not have witnessed that if this really was true. We shouldn't have seen that occur. We should have seen something in this area. But what we saw was something way out in this area. And that's what that blue box says. What we observed was so unlikely, the probability of it was so unlikely if the true parameter was 0.80 that it gives evidence that it is not true. And so really this is kind of the situation, is his claim is the null hypothesis. We suspected the alternative hypothesis, that is proportion of shots is less than 0.80. Notice I used P, but I'm going to say it. If you don't define it, you don't get to use it. So P equals the basketball player's true free throw percentage. So what we're saying is this. If the player's claim is true, then the probability of us observing what we did, 32 out of 50 free throw shots, was about 3 out of 400, we get 0.0075, less than 1%. So what we observed was so unlikely to occur, less than 1%, that it gives evidence against what the basketball player claimed. It gives evidence against that statement. Based on that evidence, we can conclude one of two things. We can say his claim is correct, and by bad luck, we happen to witness something that should not have occurred. An unlikely outcome occurred because of bad luck. That's one thing that we can use to explain the outcome. Now, the other thing is that the population proportion, what he said that he was an 80% free throw shooter, is actually less than that. And so our result was not likely to occur. It says our result is not an unlikely outcome. So the bottom line is this. This is the basic idea. An outcome that would rarely happen if a claim were true is evidence that the claim is not true. And that's a weird thing to say. An outcome that would rarely happen if a claim were true. And so, again, this distribution is assuming that the claim is true. We are assuming that he is in this area. So, assuming that claim is true, an outcome way out here in this tail that would rarely occur, 3 out of 400, if the claim were true, shows that this cannot be true. What we saw and what we witnessed should not have happened. And we witnessed it. There's a very small chance that we would. So that means his statement, there's a very good evidence against his statement, and his statement is not true. Blue slide here, so please pay attention to this because this outlines the 4-step process for performing inference using significance tests. Your state is going to state the hypotheses, both the null and the alternative, in words and symbols. Your plan still has to follow the same type of structure we did before. You need to name the inference procedure you're going to use. And you need to verify the conditions. I wonder if the conditions, random, normal, or T procedures, and independent, are the same. Interesting. If the conditions are met, you carry out your inference, which is a sketch of the graph. So, I could go back to the graph that I sketched about Mary and Lloyd. That was a distribution curve. And then calculate the test statistics. So that shows you a location on it. And then the p-value was your probability. So I think that do step we're familiar with. And then concluding, you're going to interpret results in context. And notice you need to mention the p-value, your probability, something called an alpha level, and whether you reject or fail to reject. So these are the steps for the 4-step process. And we're going to break some of these down in the next example. So we're still looking at the basketball free throw shooter, and we're looking at the null hypothesis. And the null hypothesis is that there is no difference between the claim and the population parameter. So it's always an equal. There's no difference. The claim we hope, or the claim we suspect, is the alternative hypothesis. So we use H sub O for the null hypothesis, and that's always going to be equal. There is no difference. It's equal to what the claim says it is. The alternative hypothesis is going to have either a direction or be not equal. It's what we suspect that the difference is. So the null hypothesis is a statement of the no difference. An alternative hypothesis is a statement of a difference towards the direction that we suspect. So if you look, I wrote down the word state here. This is really what your state would be. You have your null. He said his proportion for free throws is 0.80. So he's claiming his population parameter P equals 0.80. I suspected he was less than 0.80. So the alternative is that his population proportion, his P, is less than 0.80. And if I use it, I better define it. P is the long run proportion of made free throws. So before I move on, you have some information here about the null. You have some information here about the alternative. But I really want to focus on the red, the warning. Your hypothesis should express the hopes or suspicions before you collect the data. You should never, 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 never collect the data and then state your hypotheses. That's wrong. Any hypotheses you make should always be about before you collect the data. So here's how we state our hypotheses. I suspected less than, so my alternative was less than. If I thought he was better, I would say my alternative hypothesis is greater. And so these are where you have alternative. You have 3 different forms. You can have a left tail, your parameter being less than the value. You can have a right tail, the parameter being greater than the value, or you can have a not equal to for your alternative hypothesis. Your null is always equal to because it says there is no difference. So one-sided tests use words that express either larger than the null or smaller than the null. Two-sided tests do not specify a direction. They only say that there is a difference. It could be either larger or smaller. We don't care. Now, and you have this space here because you're going to be drawing these three distributions in that space. But before we get there, you need to make a note. Your hypotheses always refers to population parameters, P or mu. It will never refer to X bar or P hat. And that is really important because if you think about a multiple choice test, if you say which of the following shows the hypotheses for the significance test and you see answers with P hat or X bar, you better cross them out right away. Those should be gone because you never state hypotheses with sample. You state them always with population parameters, P or mu. So here are the three distributions that we're going to use. Like I said, you have this space up here. I give myself some more room so I can kind of talk about what these scenarios are. There is cell phone battery. So let's say a company says that on average their cell phone battery lasts, it keeps its charge for so many hours. So in this case, this would really be a one-sided less than hypothesis test, significance test. And the reason why is because I would care if my battery life was less than what they told me. If I had bought their phone and it had a battery life and it was less than what they claimed it was, I would be upset. I would reject their claim. I would reject the null hypothesis. However, if the battery life lasted longer, if the battery life was in this area, then it's where they said it was going to be. If it lasted longer, I'd be happy. And so this area we call the fail to reject the null hypothesis. Because if we have battery life that lasts longer, I wouldn't be upset. I would only be mad if it lasted less than what they claimed. So this is why this one would be a one-sided less than significance test. For this one, it looks at college tuition. So let's say after scholarships, the college tells you, hey, your college tuition on average after scholarships for our people is $7,000 after scholarships. You're like, awesome. But when would you be mad? Well, you'd be mad if it turns out you're paying $15,000, $25,000, $30,000 in this case. So this is a one-sided greater than significance test because if what you see is over in this area, you're going to be mad about it. And this is our reject the null then. But if you are paying less than what they meant, if you're paying $2,000 after scholarships, if you're in this area where they said you're going to be, you wouldn't be upset because that's what they said it was going to be. And so this would be the fail to reject the null hypothesis area. So there are times where you read it, you're going to have to figure out which side you're going on. Now, car tire pressure, it matters if you overfill or even if you underfill the air in your tires. So this is a two-sided. We don't care. Underfilled causes problems, overfilled causes problems. So if you look at it to the left here would be underfilling your tires. So this would be your reject the null area. But if you overfill your tires, you can have danger as well. And so this would also be your reject the null area because it's away from the area that says that the parameter is true. It's further away from those. And so this region would be your fail to reject the null. So notice it really has to deal with the tails, doesn't it? Because if we see something in the tails, if this were true, then it's so unlikely to have occurred that we can reject. So if something lands in this area, we shouldn't have observed that. So we should be able to reject the null. But if something lands in this area, you know what? It's bound to have happened, and it's close to what they said. So we're going to say, hey, we're going to fail reject the null hypothesis. So here are some key words to look for one-sided and two-sided. One-sided, there is a direction to the relationship that's being expressed. The keywords can be less than, greater than, lower, higher, more, smaller, less, bigger, etc. Those are keywords in the prompts that tell you you're looking for a one-sided. Now for a two-sided, no direction is specified, no direction is expressed, just that there is a difference. So some key phrases here is has the true value changed, or is there convincing evidence that the true value is different? Or even test the claim that the parameter equals the value, and no direction is given in that case. So there are key words to look for in prompts to help you determine whether you're dealing with a one-sided, a two-sided, and if it's one-sided, which direction you're focusing on. So in this problem, we are looking at job satisfaction, a study done about this. And the question is, does the job satisfaction of assembly line workers differ when their work is machine-paced rather than self-paced? And so I see right here the word defer. And that's leaning me towards right now, and I'm going to keep reading though, that maybe we're just looking at it's different. Nothing's being specified when it comes to direction yet. But let me just keep reading to make sure. So one study chose 18 subjects at random from a company with over 200 workers who assemble electronic devices. Half of those workers were randomly assigned to two groups. Both groups did similar assembly work, but one group was allowed to pace themselves, while the other group used an assembly line that had a fixed pace. And after 2 weeks, they all took a job satisfaction survey, and then they switched to the other group. They worked again for 2 weeks, and then they took that test of job satisfaction to see how it was. The response variable is the difference in satisfaction scores, self-paced minus machine-paced. This, you can kind of see, relates to your AP free response group test problem. They're specifying that you're looking for the difference in the scores, and it's telling you what way you are subtracting them. So if you don't define it, you don't get to use it. Part A is looking at describe the parameter of interest. And so we're looking at mu sub D, which is the differences. Again, you have to say which way, self-paced minus machine-paced, in context, in job satisfaction scores in the population of all assembly line workers at this company. So I defined, in this case, the variable, the parameter that we're trying to test the claim for. Now, what's my claim? Well, the claim is that there is no difference. So the claim is that there is no difference between assembly line that is fixed versus self-paced. So in that case, your difference would be 0 between them. If you did self-paced minus machine-paced, there would be no difference. So my null would be mu sub D equals 0. The alternative is that there is a difference. It doesn't say which direction, by the way, just that it is different. And so in this case, it is a not equal to. So if we keep going, what happens is a study occurred, and they got the results. And from their sample, so we have our null, we have our alternative. What their sample said was that X bar equals 17, and it had a standard deviation of 60. This was just from what they collected. Now what that means is the workers rated self-paced environment on average 17 points higher. This is what your X bar means, is that they rated the self-paced environment on average 17 points higher, because remember the order of subtraction. Now they performed a significance test using that data, and they found a p-value of 0.2302. We're going to get to what that p-value represents, and it is something you're familiar with. We have to learn how to interpret it. So right away it says explain what it means for the null hypothesis to be true in this setting, and that means mu sub D equals 0. That means the mean difference in satisfaction scores, self-paced minus machine-paced, for the entire population of assembly line workers is 0. In other words, if the null was true, if the claim that there is no difference was true, then the workers would not favor one work environment over the other on average. So if the difference was 0, the self-paced and machine-paced ratings would be close to each other. So the workers would not favor one work environment over the other on average. So we're going to look at interpreting that p-value now. And so what the p-value does is it measures the probability of the strength of evidence against the null hypothesis. That's what we call the p-value. And so the p-value is the probability against the null hypothesis. That means the smaller the p-value, it gives evidence against the null, because it says that our observed result is so unlikely to occur when the null is true. Think about the tails. If you're supposed to be in the center and we're way out the tails and have a probability on that tails, what we saw gives evidence that it was unlikely to happen if the null were true. Larger p-values are going to start to go towards the middle. And so larger p-values do not give convincing evidence against the null. Look how that is phrased, because it says the result is likely to have occurred when the null is true. So this is really kind of p-values, and that's a really hard thing to look at for interpreting. So you may have heard me say phrases before of like reject or fail to reject. And the reason why is the way you state your conclusions is really important, the way you phrase them. And we're going to look at that a little bit more later in the video, but right now think of it this way to kind of help you. Why do I say reject or fail to reject? It relates to juries. If when you have a jury and they make the decision, they say, we, the jury, find the defendant guilty or not guilty. They do not say, we, the jury, find the defendant innocent. Why not? Think about it this way. Could someone be found not guilty and still have committed the crime and gotten away with it? So does not guilty mean that they are innocent? And so phrasing is really important here. Think of it this way. This might relate to something you might be familiar with. Who knows? If you ask someone to prom, there's some possible responses. Oh, absolutely, you're the love of my life. No way, jerk. Or I'm not saying no. So the person who tells you, I'm not saying no, is that the same as them saying yes? And we could even think of this like the Lloyd and Mary situation that I'm still waiting for the response for. She could love him more, the same as he does. Hey, you're the love of my life, Lloyd, and yeah, I know that could happen. She could not love him because it's only been a week and say, no way, jerk. Or she says, this is kind of awkward. Is her saying this is kind of awkward? Does that mean the same thing as yes, that she does love him? So keep this in mind on how you say your conclusions. So part D asks us to interpret that p-value 0.2302. And that p-value is the probability of observing a result as extreme or more extreme in the direction of our alternative hypothesis, just by chance if the null was actually true. And it's a very weird thing for the interpreting of p-value. And I'll show you what it means visually. But you probably need to write down some of them and get used to it, just like you do for some other interpretations. So because the alternative hypothesis is two-sided, the p-value here is the probability of getting a value of x bar as far away from 0 in either direction as we observed x bar equals 17 when the null is true. So in other words, on average, the average difference of 17 or more points, that's more means towards the tails, between the work environment would happen 23% of the time just by chance in random samples of 18 assembly line workers if the null was true, if there was no difference. And what that means is our outcome, 0.2302, about 23%, that's about 1 out of 4. If the null is true in this case, there is not convincing evidence against the null. We fail to reject the null hypothesis. We fail to reject it. Don't say it's true. We fail to reject. Now, it's a very weird thing to interpret your p-value. So I want to look at it like this. And so think of it this way. This distribution represents your population. And so this is what the claim is. And it's either going to be mu or it's going to be p, always about a parameter. What we observe could be out in the tails, and it could be over in this area. So what we observe, maybe this is my x bar or my p hat. And what happens is, or more extreme. And so this shaded region represents my p-value. And the relationship of that p-value to the rejection level, which we're going to get to, there's going to be some level that we're going to set for rejection that we're going to call alpha. The relationship of that tells us what to do. But what I want you to realize is this is your interpretation of p-values. So let's kind of go through what we said in the previous slide. If the parameter is true, if the null hypothesis is true, the probability of us getting the result from our sample that we did, the probability of us getting that result or more extreme just by chance. That's your p-value. Our p-value is the probability of seeing what we observed if this were in fact true. So your distribution that you're going to sketch is based off of the parameter being true. you're plotting your sample. And your p-value is the probability of that sample occurring in the true distribution. So that's really what we were saying here. The final step for a significance test is your conclusion. And when your conclusion, there are two decisions that can be made based off of that evidence, based off of that p-value. And it's either reject the null or fail to reject the null. If our sample result is too unlikely to have happened by chance, assuming the null is true, then we reject the null. Otherwise, we fail to reject the null. A fail to reject the null in a decision does not mean the null is true. So for that reason, you should never, ever, 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 never accept the null. Don't be that student who accepts the null. And so really what this means is this. If your probability is small, it's in the tails, which means you're observing something that should not have occurred. So the null, you can reject it. And so you're going to conclude in favor of the alternative. If the p-value is large, you're coming towards the inside, which means you're seeing something that could occur by chance. So you fail to reject the null, so that means you do not have enough evidence to conclude the alternative. You never, never, never accept the null hypothesis. And so how do we determine when we reject or when we don't reject? And that's called a significance level. And we use the Greek letter alpha to help us. And with our p-value, if it's less than that chosen alpha, then we say our result is statistically significant. So if you're not told what your alpha level is in the problem, use 0.05, but you could be told, and that is set. So if our p-value is smaller than alpha, that means our probability of our sample is way out of those tails, and we could say it's statistically significant. In that case, we reject. If the p-value is larger than the alpha, then we fail to reject. But if we reject, it's in favor of the alternative. So, same idea as the last slide you can see on the bottom here. If your p-value is less than your significance level, alpha, you reject the null, you conclude the alternative because you're out in those tails. If the p-value is greater than or equal to your alpha, you fail to reject the null, don't accept it. The null hypothesis, fail to reject it. Never admit you're wrong. And you do not have enough evidence to conclude the alternative. So we're going to use this example of better batteries to help us understand better the relationship of p-value and significance level. In this example, a company has developed a new deluxe AAA battery that's supposed to have a longer battery life than their previous AAA battery. The problem is these batteries cost more to produce. And by the way, right off in this first sentence here, it says it's supposed to last longer. So when I'm reading the prompt, I'm thinking my alternative has to be greater than, because they're supposed to last longer. So that's where I'm leaning right now. I'm going to finish reading the prompt here. So they want to be convinced, because it costs more to make these new deluxe AAA batteries, that the lifespan of these batteries is for sure longer. So what do? Is they collect a simple random sample of 15, and they run them continuously until the battery is drained, and they do a significance test. And here's the significance test. The null hypothesis is what their previous version was. They had 30 hours of life in their previous AAA batteries. The alternative hypothesis is what they want. Hey, these new ones are supposed to last 30 hours longer. So they want them to last longer because it does cost more to produce, so they want to guarantee what they're saying. So the alternative hypothesis is that your mu is greater than 30 hours. Notice those are parameters. And if I'm going to use mu, I better define mu. Mu is the true mean lifetime of the new deluxe AAA batteries. Now, when this significance test was done by the company, they got a p-value of 0.0276. So you can see right here, I have a distribution, and that distribution is based off of the claim that the population is true. So what this distribution is saying is, and I'll make it a little bit thinner, that this is true. That, hey, your mu equals 30. I mean, that's what that's saying in the middle. So if it's true, what do we find out? Well, from the sample, we said greater than, so that's making me think that's over on the right-hand side, right? Because we were doing greater than. And when they got their sample, they got some X bar here. We weren't told what it was. And boom, 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 there's the shaded region. And we're being told the area of that shaded region is 0.0276. So the p-value in this region is 0.0276. That's the area in that tail. So keep that in mind. So that's what we're looking at. Now let's read the rest of the problem. So what conclusion can we make at the alpha, the rejection level, significance level, of 0.05? So think about this based off what we did before. Here are the three types of hypotheses and tails we could have. This one looks like it is a right-tailed one. So we're going to have a rejection level, a significance level, and that's going to be based off of your alpha. So when I'm looking at in this case, I'm going to go ahead and say, well, if my area to the right of that x bar that I found is 0.0276, then what does that mean when it comes to your significance level? Well, my significance level is based off of alpha being 0.05. So that means I would have 5% to the right. That would be, hey, to the right is my rejection level. To the left is my fail to reject the null. So to the right, if it lands solely in that right side, I reject the null and I can conclude the alternative. If it lands over here on this side, well, that means it's towards what they said, the original null hypothesis. So I'm not going to question anything. Well, in this case, that entire p-value is in the rejection area. And again, look at the three things that we drew. If it is completely in this area here, you're going to reject the null hypothesis. So in this case, since the p-value is less than, so that's what happens. My p-value is 0.0276, it's less than my alpha, I am going to say the sample result is statistically significant at that 5% level, the alpha level. We have sufficient evidence to reject the null, and therefore we can conclude the alternative, that the company's deluxe AAA batteries, the new ones, do last longer than 30 hours on average because it's mu. And so keep that in mind as we reject the null, which shows sufficient evidence to conclude the alternative. And the alternative was that the average lifespan was greater than 30 hours. And 5% is our significance level. So the fact that we can reject the null means our result was statistically significant because it's way out in the tail. It shouldn't have happened. But what happens if I take that significance level and I make it even smaller? So right now, if I look at this significance level was 0.05. The area to the right of it is 0.05. But what if I were to take that significance level and make it, we'll do this, 0.01. Well, that's a smaller area, isn't it? So that means I got to take this, I'm going to slide it, and it's 0.01 is actually smaller than 0.0276. So in this case, notice my x bar is outside that rejection area. I'm in the fail to reject the null hypothesis area. So in this case, when I have that smaller significance level, the p-value is greater than my alpha level 0.01, which means the sample result is not statistically significant because it's going towards what we thought it was going to be, mu equal to 30, what the claim was. So we do not have enough evidence to reject the null. So we fail to reject the null is what we can say. So in other words, we do not have enough evidence. We cannot conclude that the deluxe batteries last longer than 30 hours on average. So again, you never accept the null hypothesis. You have insufficient evidence to conclude the alternative. Don't admit you're wrong. You have insufficient evidence to conclude the alternative. The point of this slide is to realize what the role of the significance level is and how it plays in either rejecting or failing to rejecting, and what happens when you change your significance level. It could change the result. It's the same study. They're both dealing with the AAA batteries, but in part A, we rejected the null, and we concluded the alternative. In part B, because we lowered the significance level, we failed to reject the null, and we did not have enough evidence to conclude the alternative. So to recap here at the end, what we learned so far in this video was to state the correct hypotheses, the null and the alternative, and that they're based off of parameters. We also looked at the idea of left-sided versus right-sided alternative hypotheses and two-sided alternative hypotheses. And we also looked at interpreting p-values and the relationship it has with your significance level. That could be Lloyd, because we have yet to figure out how it went with Mary. So give me 1 second and let's figure this out. Turns out he sent me a video of it. So I won't leave it hanging. What I'm going to do is I'm going to play the video for you. So give me 1 second to hook it up.
What do you think the chances are of a guy like you and a girl like me ending up together?
This is the moment.
Well, Lloyd, that's difficult to say, and we really don't...
Hit me with it. Just give it to me straight. I came a long way just to see you, Mary. Just, least you can do is level with me.
It's true.
What are my chances?
Not good.
You mean not good like 1 out of 100?
I'd say more like 1 out of 1,000,000.
Oh, rejected. Wow.
So you're telling me there's a chance?
So as you figured out, there really is no Lloyd and Mary, a friend. Really, we're looking at Lloyd and Mary from Dumb and Dumber. And the idea, though, behind it is that kind of simple to think about rejecting versus failing to rejecting, and even significance level. Because Mary said the p-value is that Lloyd had a 1 in a million chance. So the p-value Mary said was 0.000001. All right, now you heard me say, oh, rejected. Because, man, 1 in a million chance of getting together, I would say, you're rejecting. But what does Lloyd say? So you're telling me there's a chance. So if we take a look at this, this is really where Mary does not love Lloyd as much as Lloyd loves her. Her love is less than Lloyd's. And so when you're looking at this, which is the level that Lloyd chose? Because Mary rejected him. But Lloyd says, hey, there's a chance. And so if I'm looking at it, I see right here in this alpha level of 1, that's got to be, that would be a level where like, hey, you would reject because that is in the rejection area, the significance level. But what did Lloyd say? He said, hey, there's a chance. So Lloyd changed his alpha level so that way he could say, so you're telling me there's a chance. So what happens here is Lloyd saying his alpha level is actually larger than what Mary said. So Mary said, hey, there's a 1 in a million chance. Not good. But Lloyd's like, you know what? I'm just going to set my alpha level to be way smaller. And that way you could fail to reject me. So it's just meant to be fun with this idea of the alpha level, the significance level, reject, fail to reject. But really is meant to also help you understand the further you are out in the tails, Lloyd wants Mary to like him as much as he likes her. So he wants to be in the middle. But the further that it is out here, the more of the chance that Lloyd's going to be rejected. So it's a way to kind of make it easy to understand rejecting versus fail to rejecting.